you'll have a jury back on Wednesday, and hopefully you can bear my British accent. Okay, so I understand that you guys have been learning how to differentiate specific functions using the limit definition of derivative. And on Friday, you learnt an alternative limit definition of the derivative. So before I motivate today's lecture, can someone remind me the definition you learnt on Friday? So you have the derivative of a function f of x is the limit as h goes to 0 of 1. So the limit of f of x plus h minus f of x all of x. So this is the definition you learned on Friday. I'm going to leave this up here for the lecture because we're going to need it quite a bit today. Now, I want to, before looking at anything general today, recap some specific examples. And you'll see why I'm going to choose these specific examples. So, suppose you had x to the power of 0. What's this derivative? So what is x to the 0? And the derivative of 1 is derivative of 1, 0. Okay, let's write x to the power of 1. So that's just x. And the derivative of x is 1. You've also found the derivative of x squared. Can anyone remember what the derivative of x squared is? Okay, now suppose that I go to something like, I don't know, x to the power of 48. Any ideas how to differentiate it? We'll get to that. But in general, you can see that they're not going to want to put this into that formula every time, because it's going to be horrible expanding something like x plus h to the 48. So what about derivative of x to the n, or any number n, okay, so why do we even want to find this derivative? Well, for a start, it'd be nice to have a simple formula to use so that you don't have to keep wasting time using this definition every time you want to find a derivative. So, x to the n prime is useful for differentiating well, there are lots of things it's useful for differentiating, but one might be polynomials. So I'm sure you're all familiar with polynomials, so you have something like p of x is x to the power of 5 minus x to the power of 4 plus 3x squared minus x. It's going to be an awful pain if you have to keep putting this into that formula. In a nice simple rule for differentiating x to the n, you can just write down the derivative of this. The other thing it's useful for differentiating are what we call inverse parallels. So it's also useful for differentiating inverse parallels. So an inverse power law just means that you have a negative power of x. So this might be something like f of x being 1 over x squared, which is just x to the minus 2. And these kind of functions are particularly useful because they describe a lot of physical things like gravitational and electrostatic forces. So you can imagine if you do any physics, you'll have to differentiate a lot of these. Okay, so before we look at x to the n, let's look at a specific example that will show us the method that we need to derive this formula. So, example. We use f of x equals x cubed. So n equals 3. And the derivative of x cubed is what? Using the definition we've got up there, what's the derivative of x cubed? Or we'll start with the limit definition. So it's the limit as h goes to 0 of what?
X plus h cubed
X plus h cubed
minus x cubed
minus x cubed
over h.
all over h. Now to find this limit, we're clearly going to have to do something with this x plus h cubed to make it something simple that we can actually take the limit of. Because if you put x equals h straight in there, h equals 0 straight in there, you're going to get 0 divided by 0 as always. So we expand x plus h cubed. So any ideas how we're going to expand x plus h cubed? Any ideas? Well, we're going to try and avoid using binomial expansion, so we don't have to know the formula. But in general, how would you expand a set of brackets? Or what can you factor out of this? I can hear the right answer somewhere. Anyone? I keep hearing x plus h. So if we take out a factor of x plus h, we've got x plus h times x plus h squared x plus h, we know what x plus h squared is. X squared plus 2hx h squared. Multiply this out, and we've got this times this gives us x cubed plus x times 2hx gives us the 2hx squared plus those terms multiplied gives us xh squared. And the same thing with the h's. So we've got xh squared, hx squared, sorry, plus h times 2hx gives us 2h squared x, and the last term is h cubed. And now we can just plug that straight back into our formula up there. So now the derivative of x cubed is the limit as h goes to 0 of this x cubed plus, sorry, if we simplify this first, so we have 1x cubed, group together all the terms are the same, so we have a 2hx squared plus an hx squared gives us 3hx squared. Similarly, we've got an xh squared plus a 2xh squared, which is a 3xh squared, or h squared x, and then h cubed. So if you put that back in here, we've got x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed, all divided by h. And now we can see that our x cubes cancel, and now we can find this limit. So what do we do to find this limit?
You'd want to factor out the x's from the first one, probably.
Not the x's.
Oh, then the h's. Oh yeah, the h's, so then you can cancel it as denominator.
Yes, exactly. So you can see that all these terms in the numerator now have at least one factor of h. So we can divide through by this h, which leaves us with the limit of 3x squared plus, so that's this term divided by h. Divide that term gives us a 3xh plus h squared. So the derivative of x cubed is, someone shout it out, 3x squared. Now, I want to point out at this stage that if you look back at this expansion that we had of x plus h cubed, in the end, all we needed were the first two terms. So we needed the x cubed term to cancel with that x cubed term, and then the second term we have here, the 3hx squared, became the 3x squared term. All the other terms disappeared. And that's going to become useful when we look at n instead of 3. So now let's look at f of x equals x to the n. So let's approach this in exactly the same way we did before. So derivative of x to the n is the limit, as h goes to 0, of what is it the limit of? So what's our f of x plus h here?
X plus h to the n
X plus h to the n
minus x to the n over h.
And then just like we needed to expand x plus h cubed, now we need to expand x plus h to the n. How are we going to do this? And yes, if you know the binomial theorem, you could use that. But if you don't know the binomial theorem, how are we going to expand this? Any ideas? Well, let's do the same thing we had for x plus h cubed. So if you just write out all these factors. So we've got x plus h times x plus h and so on. And here we've got n terms. So now how are we going to multiply this out? If you've got a set of brackets, how should we expand out this multiplication? How do we open the brackets? Sorry?
We can't really, because you don't know exactly how many we're expanding.
Well, we know that we've got n factors here. So just like when we multiply out of open any bracket, we want to multiply each term in this bracket by each term in this bracket, each term in this bracket, and so on. So if you multiply this x by this x by this x, and so on all the way to here, so we multiply all the x's together. And we know that we've got n factors of x here because we've got n brackets. And then the same thing if you multiply this h by all the x's. So we have h times all our x's. Then we can do the same thing with this h. So if we multiply this h by this x and that x and all the other x's, so we've got x, h, x, and so on. And we can do that for each one of the h's. I remember we've got n h's here. So we're going to get lots of terms, well, n terms that involve one h and n minus 1 x's. Then we're also going to get some terms where, let's look at two of the h's. So we might multiply this h by this h, by this x, and all the other x's. So we've got h times x, and so on. But then we might multiply, I don't know, this h and this h by this x and all the other x's. So you've got a term that looks like x, h, x, and so on. And you can see we're going to get a lot of terms that involve lots of h's and x's. I'm not going to write them all out, and you'll see exactly why. But there's one more easy term we haven't got, which is this h times this h times this h, all the way to the last h. And so on. And now we want to group together all the terms the same. So the first term over that is just x multiplied by x n times. So that's going to give us an x to the n. And then our second order, we have terms over here where we have h times n minus 1 lots of x. Here we've got another h times n minus 1 lots of x. And remember, there will be one of these terms for every h we have here. And we've got n h's. So we're going to get n lots of these h times x to the n minus 1 terms. That's n h x to the n minus 1. And then again, we've got a lot of terms that involve two h's multiplied by n minus 2 lots of x. And we don't really care how many of these terms we've got. And that's because if you look at when we did the x cubed example, we only needed the first two terms because all the others disappeared when we took the limit. And exactly the same thing is going to happen here. So we will have something times h squared x to the n minus 2 plus, and then we will have lots of similar terms with h cubed, h to the 4th, and so on, all the way up to h to the n. So for example, if n was 4, if you have x plus h to the 4, if you work all this out, you would get x to the 4 plus 4 x cubed h plus 6 x squared h squared plus 4x h cubed plus h to the 4. So for any value of n, we can always work out what all these terms are and what all the coefficients are. But the reason I'm writing it like this is because, as I said, only these first two terms are going to matter. Is this clear to everyone? Any questions on this? Okay, so now we can substitute this back into our formula that we have over there. So now the derivative of x to the n is the limit as h goes to 0 of, plug this back in for x plus h to the n. So we've got x to the n plus n h x to the n minus 1 plus something times h squared x to the n minus 2 and so on all the way up to this h to the n term. And then we have minus x to the n all divided by h as usual. And now we can see that our two x to the n terms cancel, just like our x cubed terms cancelled before. And all these terms in here that aren't written down depend on h, just like we did in x to the 4 here. So how do we find this limit now? Factor out the h's. So when we factor out all the h's, divide all these terms through by h, and we're left with, well, this is going to give us n x to the n minus 1 plus something times h times x to the n minus 2 and so on, and the last term here is going to give us an h to the n minus 1. So what is the derivative?
nx to the n minus 1.
Yes. So all these terms disappear, and this is exactly why we needed to write out all these terms, because they're all going to disappear at the end. So we're left with nx to the n minus 1. So the derivative of x to the n is just nx to the n minus 1. And now you no longer need to keep using a horrible formula, limit definition, to work out this derivative. Now, we've assumed here that n was a positive integer. Otherwise, we wouldn't have been able to expand x to h to the n quite so easily. So what you'll actually find is that this is true for any value of n. It's not just true for positive integers n. N could be a negative integer, or it doesn't even have to be a whole number. And you can still prove it using the limit definition. It takes a little bit more time. So this is true for all numbers n. True for all numbers n, not just positive integers. Okay, so let's look at some examples. try n equals 2. We already know what the derivative of x squared is, so we should get the same thing back. So f of x is x squared. So what's the derivative of x squared using our new formula? Yep, so we have n is 2, n minus 1 is 1, so we have 2x, which is exactly what we had before. Now let's suppose that we had n equals 3. So we've just found the derivative of x cubed, so we should get the same thing again. So f of x is x cubed. So f prime of x is what? 3x squared. And it's exactly what we found over on that board. So we know it works. Okay, so let's try a slightly more difficult example. Suppose now that we had f of x is 1 over x. A few lectures ago, you found the derivative of this using the limit definition. So now we're going to find the derivative of it using the power rule that we have. So how can we write 1 over x in a way that we can use our new formula?
X everyone.
Yes. So 1 over x is x to the minus 1. So f prime of x is equal to what? Yep.
Minus 1 x to
Yep. So n is minus 1, so we've got minus 1 x to the minus 2, which is
minus 1 over x squared.
minus 1 over x squared. And if you look back in your notes, you should find that this is the same thing you got when you use the limit definition. So I said that this works for even negative values of n, and here we've seen that it definitely works for n is minus 1. So now what if we had f of x equals 1 over x to the 3 over 2. I can write this in a form that we can use the power rule. Yes. So this is x to the minus 3 over 2. So if we use the power rule, what's its derivative? Well, we've got n is now minus 3 over 2. So what does our power rule tell us the derivative of this is?
Minus 3 over 2x times minus 5 over 2.
Yep. So we've got x, n is minus 3 over 2, n minus 1 is then minus 5 over 2, and then we can write this back in the original way. So you've got minus 3 over 2, and x to the minus 5 over 2 is just 1 over x to the 5 over 2. So that's minus 3 over 2x to the 5 over 2. So now let's look at another rule that you're going to need if you want to differentiate things like polynomials, where you have a sum of terms. So here we're doing derivative of a sum. So the goal here is we have two functions, f and g's. We add them together, take the derivative, and we want to know what this derivative is. So there's an intuitive way that we can think about this derivative, and that's to say, suppose that you have 2 buckets of water, and you're going to simultaneously pour them both into a bigger bucket. So some of this water is going to come from the left bucket. And some of it's going to come from the right bucket. And now how do we interpret f and g? So in this example, f and g are going to be functions of time as opposed to x. So we'll have f of t and g of t. So f of t will just be the amount of water that we've poured out of the left bucket after time t. And g of t will be the same thing, but this is going to be the amount of water we poured out of the right bucket in time t. So the total amount of water in this bucket is just f plus g. So f of t plus g of t. So now the derivative of this is just going to be the rate of change of the amount of water in this bucket, because we know that a derivative is just the rate of change. So this, the derivative of this, will just be the rate at which we fill this bucket up. So we'll say that f prime of t, well this is just the rate of change of f, which is just the rate at which we're pouring water out of the left bucket. So we'll call this the pouring rate from the left. And the same thing for g. So the derivative of g is just going to be the rate of change of g, which is the rate at which we're pouring water out of the right bucket. So the pouring rate from the right bucket. So now, the derivative of f plus g, this is the rate at which we're adding water to this bucket. So that's going to be the rate at which we're adding water from the left, plus the rate at which we're adding water from the right. So the derivative of f of t plus g of t is the rate at which we pour from the left, that's f prime of t, plus the rate at which we pour from the right, which is g prime of t. So just to make this clear, suppose that you're pouring water from the left at maybe 2 litres per second. Let's suppose that you're pouring water from the right at 1 litre per second. So G prime of T is 1 litre per second. Then this means that you're pouring 2 litres of water out of here every second, and you're pouring 1 litre of water out of here every second. So every second, in this big bucket, you're going to get 2 litres from here, and 1 litre from here. So you're going to fill this up at 3 litres per second. So this is going to be 3 litres per second. Is that clear? Any questions about any of this? Okay, so let's combine the two things we've learned into an example. Suppose that our function is f of x equals x to the power of 4 plus 2x squared. So what's its derivative? Well, we've got the power rule. Well, we've got the derivative of a sum to break this up, and we've also got the power rule. So what's the derivative of this function going to be?
4x cubed plus
4x cubed plus 4x. Yes, we just differentiate each term separately, and we've got our power rule to differentiate each of the individual terms. So we've got the derivative is 4x cubed plus 4x. Let's look at another example. Suppose that f of x is 3x to the power of 5 minus 1 over x squared. What's its derivative going to be? Well, we can use the rule for derivative of a sum. What's the derivative of the first term?
15x to the 4.
15x to the 4. Let's rewrite this in a way that we can use the power rule on both terms. So we've got 3x to the 5 minus, how should we write 1 over x squared?
X to the -2.
X to the minus 2. So its derivative of the first term, 50x to the 4. What's the derivative of the second term?
Negative 2x cubed.
So we've got derivative of x to the minus 2 is minus 2x to the minus 3. And if we simplify this, we've got 15x to the 4 plus 2 over x cubed. Now let's look at a slightly more applied example. we want to find the points where the tangent line to y equals x cubed minus 27x are horizontal. Okay, well first, what does it mean for the tangent slope to be horizontal? So, if the tangent line to a function is horizontal at a point, what can we say about its slope? So the slope is 0. Okay, so what is the slope of the general function at a point x? So if you take any point x, what is the slope of y x? Any ideas? So if we wanted to find the slope of, so suppose we wanted to find the slope of a function y equals f of x at x equals a, what is the slope?
The derivative.
Yes. So the slope of this would be f prime of a because we're evaluating it at x equals a. So the derivative at any general point, the slope of the tangent at any general point x will just be the derivative evaluated at x. So the slope of our function is dy by dx. So what is dy by dx in this example? Sorry? 3x squared minus 27. And we want the points where the slope is 0. So slope equals 0 means that this is equal to 0. We can just solve this. So 3x squared is 27. Divide through by 3. X squared is 9. So, first, how many points is the tangent line horizontal for this function?
2.
And there are x is plus or minus 3. But we haven't finished yet. We've got the x values, but we want the specific points. So we also want the y values. So how are we going to find the y coordinates of these points? Sorry? Yep. So we can put these points back into our equation over there. So we've got the y value of x equals minus 3 velocity is going to be minus 3 cubed minus 3 times 27. And if you work that out, you will just get 54. And the same thing for the other one. Y value at x equals 3. Well, that's just going to be 3 cubed minus 3 times 27. And you find that this is minus 54. So the tangent line is horizontal at the 2 points where we've got minus 354 and 3 minus 54. And this makes sense if you think about the graph of x cubed. So you know roughly what a cubic graph looks like. Something like this. Well, now we know that this point, minus 3, 54, and that point is 3, minus 54. Okay, so today you've seen the power rule, the rule for differentiating the sum, and next time you'll see how to differentiate the product of two functions, which isn't quite as simple as differentiating the sum of two functions. If you came in late, your marked midterms are at the front of the class, so you can come and pick them up. Instead of these into 4 piles, 5 surnames, so I'll write down what the 4